So apparently some person is making ice cream, and they have to turn this crank handle. Okay, let's make it out like this so we can see that it's going in a circle. All right, so we're looking at it obliquely, and so here's the radius of the circle here, and it's going to go around in a circle like this. Got that? So the crank handle's doing that. Now, we are applying a force this way, a force that is constant. What is the what's the magnitude of that force? How many? 22. All right, now it's going around this circle, right? Going all the way around this circle. And is it, what do we give it? The period? Once every 1.3 seconds or something?
Yeah.
T is equal to 1.3. That's not correct. T is equal to 1.3 seconds. And this is number 56.
What do they mean by what is the average power expended?
Power expended, developed. Power is the rate at which work is done. Okay? The rate at which energy is expended or the rate at which work is done. That's our definition. So if we go back to the definition of power, all right, oh wait, we got one more thing, and that is that this radius is equal to something weird, like 1.3 meters? 0.28? Same thing. 0.28 meters. Now that's all weird looking. So just so we can see it, we'll make it a different color. Red. There we go. Radius is equal to 0.28 meters. All right. So now, how are we going to find this? Look, this was one of those alternate definitions of power that I gave you, or the idea of instantaneous power. Power is equal to the time rate at which work is done. Right? In calculus, power is dW dt, but for our purposes, we'll just do it like this, over here. We won't worry about as a derivative. All right, so if we say that power is equal to work over time, how do we determine the amount of work that's going to be done in terms of a force? Force times distance. All right, so now we know that work is equal to force times distance. So now let's be technical here. Force dot D, right? But what does it say about the force and the direction that it's always being applied? It's parallel, so it's perpendicular to the radius, or it's tangent to the path, so it's always in the same direction as the instantaneous displacement, which is going to be tangent to the circle. So we don't have to worry about cosine of anything or at all, do we? Right? Because cosine of 0 is going to be 1. So it's just going to be FD, force times distance, here still over time. This is where we get a little bit tricky. We could say that power is equal to force times distance over time, or we could say that power is equal to force times distance over time. Exactly. So here power is going to be force times velocity.
Oh my God. Wow.
All right? So really we're going to do the same math no matter how we do it, because we've got a distance and we've got a time. So we're going to put all those in anyway. All right, but this is the type of problem where you can use the force times velocity paradigm. All right, so we know the force, and we know the distance is going to be equal to 2 pi times the radius over the amount of time that we're given. Well, I'm going to make it a capital T because we're talking about the period of rotation around a circle. Okay? So now it's just a matter of plugging all those in. So we could say, you see how this right here would be velocity? This would be the average speed, 2 pi r over t. That's our definition from before of the speed, tangential speed of an object moving in a circle. All right, so now all we have to do is plug in that information. And so power, somebody's got a calculator out, work it out for me right now, right, Matt? So force is, what was it? 22 newtons times 2 pi times a radius of 0.28 meters. And we're going to divide that by our time, which was 1.3 seconds. All right, so now power. Here we go. What are we going to do here? I'll give you a hint. It's going to be green. Dimensional analysis. All right, what are the units for power? The units of power are what? Are what? Yes. The correct answer is yes. The units of power are what? Yes. All right, so how do we find the units of, how do we find power or watts in fundamental terms? 1 watt is equal to a joule per second. A joule is a Newton times a meter per second. A Newton is a kilogram meter per second squared times a meter divided by seconds. A watt is kilogram meter squared per second cubed. That is watts in fundamental unit. Okay? So now let's see how we're doing. Now we could actually make this a little bit easier because we can see right from here, from this step here, that's what we have up here. We have Newton meters per second. Okay? And if we broke that all the way down, we get down to kilogram meters squared per second cubed. But we can be confident that this number, we've got this set up correctly because it's dimensionally consistent with what we need for power. All right, so now plugging all that stuff in, what do we end up with? 29.7 watts? Watts. All right, so power is equal to 29.7 watts. All right, that's the amount of power. So now listen, if we had, let's say we had a machine that could crank that handle, and that machine was a 30-watt machine, it could do this, couldn't it? Right? In other words, it would be expending 30 joules almost 30 joules every second. If we wanted to make it crank faster, we would need a more powerful engine or a more powerful motor to do the same amount of work in less time, or apply the same force times a greater velocity, because that would take less time, wouldn't it? Does that make sense? All right, so this is all consistent with what we would expect.